Good evening, everybody. Welcome to Conway Hall, the home of ethical thought. The Conway Hall Ethical Society, or the South Place Ethical Society, as it used to be known, has been around for a long time. It's the longest established ethical society, I think, in the UK. It's the home of ethical thought in the UK. And this evening, we are going to talk about machine learning systems. Today's machine learning systems are trained by data. They're so effective that we've invited to see and hear them for us and to make the decisions on our behalf. But what if the systems that we attempt to teach will not, in the end, do what we want or expect? There could be consequences, both ethical and potentially existential even. Researchers call this the alignment problem. Our speaker this evening, Brian Christian, is author of a couple of bestsellers, The Most Human, which was on the New York Times Editor's Choice and a New Yorker favorite book of the year, and Algorithms to Live By with Tom Griffith, which was an Amazon Best Science Book of the Year and MIT Technology Review Best Book of the Year. His new book is The Alignment Problem: How Can Machines Learn Human Values? He's going to speak to us for about 45 minutes, and then after that we'll have Q&A. So please do type in the chat window and make comments and ask questions. We'll get to them later. Meanwhile, I'd like to hand over to him for Ethical Matters, Machine Learning and Human Values.
Thank you very much, Deborah. It is a great honor to be able to address Conway Hall Ethical Society, all the way in this case from San Francisco. So it's a great pleasure to be speaking with you. And let me share slides here as I begin. Okay. I believe that the development of artificial intelligence, and in particular, as Deborah mentioned, machine learning systems, which are systems trained by examples from humans. The development of this technology in the last 10 years has brought us to a critical ethical juncture. But the story of the present juncture really begins, I would say, in the year 1923, when a young boy named Walter Pitts is running down the street in Detroit, Michigan, to escape a group of bullies that are attacking him. And he runs into the public library and he hides to take shelter. He hides so well, in fact, that the library staff don't even notice he's there, and he is locked inside the library for the night. He pulls a book off the shelf and he begins reading it, and he reads it cover to cover. The book is a 2,000-page treatise on formal logic by Cambridge University's Bertrand Russell. And Walter Pitts decides to write Bertrand Russell a letter telling him how much he liked the book, but also that he's found several mistakes in the text. He gets a letter back postmarked from England several weeks later from Bertrand Russell saying, "I have no idea who you are, but there is a place available for you at Cambridge if you'd like to do your doctorate working with me." Unfortunately, Walter Pitts has to decline Bertrand Russell's offer because at the time he is only 12 years old and in the 7th grade. The story of Walter Pitts is really an incredible one. He grows up in a really troubled home and runs away from home at the age of 15 and moves to Chicago, where he is for many years homeless, living on the streets and dropping into lectures at the University of Chicago. He ultimately befriends the great neurologist Warren McCulloch, who essentially becomes his foster father and takes him in to his house to live with him. And the two of them begin, I think, what is one of the most kind of seminal and foundational collaborations in the history of artificial intelligence. Walter Pitts, this formerly homeless teenage logic prodigy, and Warren McCulloch, this celebrated mid-career neurophysiologist. Together, they start to think about the brain as a kind of logical machine. Could you build really simple kind of mathematical representations of neurons that would just add up their numerical inputs, and if they were greater than a certain number, they would output a number. If they were lower than that threshold, they'd output nothing. What they begin to realize is that even with these incredibly rudimentary models of actual human neurons, if you wired them together sufficiently, they could approximate any function that you could do using Boolean logic. The question, of course, was how to actually configure them to reach this promise. So this begins really the story of what we now know as neural networks and machine learning. And to compress this entire history of the field into a single slide, essentially the intuitions that Walter Pitts and Warren McCulloch have in the early 1940s are exactly correct, but they are 70 years ahead of their time. There are some celebrated milestones in the late 1950s where Frank Rosenblatt is able to create what's known as the Perceptron, which is a device based on this neural network architecture that can recognize basic shapes. And this is shown to the press with great fanfare, only to have the field essentially give up on the idea in the 60s. It's then rediscovered in the 80s and then abandoned again in the 90s and the 2000s. And then finally, it is rediscovered a third time, this time for good, in the year 2012. And I've tried to capture here as close as I can to what I consider the exact moment that neural networks really came of age. So this is at a computer vision conference in Florence in October of 2012. A young grad student from the University of Toronto named Alex Krasevsky demonstrates that he's been able to train a neural network on this task, which is image classification. Looking at what an image contains and trying to determine which of 1,000 different categories that image actually belongs to. This had been a long-standing project in the field of machine learning. And here we can see what I think is just an undeniable proof that something major has changed in the last 10 years. So you can see that from 2010 to 2017, the error rate of computer models on this task has fallen tenfold, from 30% to now significantly less than 2%. And it is really this 1 year between 2011 and 2012 that everything changes, essentially overnight. Now it is the case that these sorts of image recognition models are so good that they have become inextricably woven into, at this point, the very act of taking a photograph. So this is a slide from one of Apple's keynotes showing that there are, in fact, 11 different stages of machine learning that are operating behind the scenes every time you take a photograph now with a modern phone. It's calculating the auto exposure, the white balance, the focus, the noise reduction, the highlights, et cetera, all using this technology of neural networks that was first imagined in the 1940s. And so we're now beginning to live in this uncanny world where you literally cannot take a photograph without relying on your phone having some comprehension of what it thinks it's seeing and how it thinks that should look. Now, this has some, I think, considerable ethical implications, because a system this powerful that can learn seemingly anything based on the examples it's given is then at the mercy of the examples on which it's taught. And there is a very famous example, which I think will be familiar to at least some of you, that happened in the year 2015, where the software developer Jackie Alcine was using the brand new version of Google Photos that was using these deep convolutional neural networks to do automatic image captioning. And it was with some horror that he discovered that there was an album of photographs of himself and one of his friends that Google Photos had automatically captioned gorillas. So there's a second, I'm gonna leave this hanging a little bit. There's a second trend that has been going on for the same period of time, about 100 years, that really begins in the 1920s, but accelerates incredibly in the last 20 years. So this is the use of statistical machine learning algorithms in these kind of critical societal decision-making pipelines, in particular in the criminal justice system. Statistical models being used to predict whether someone would behave, law-abidingly if they were released early from prison. These have been in use. They were developed in the 1920s. They've been in use in the United States beginning in the 1930s. But as you can see, it is really only in the last several decades that their use becomes absolutely widespread. And for me, the best illustration of this point comes from U.S. Supreme Court Chief Justice John Roberts, who a few years ago was visiting Rensselaer Polytechnic Institute and was interviewed by the president, Shirley Ann Jackson, who asked him, can you foresee a day where artificial intelligence becomes an inextricable part of courtroom fact-finding, or even more controversially, judicial decision-making? And he responds, yes, I can foresee a day when artificial intelligence becomes a part of that process. That day is here. And so this has started to raise alarm bells in kind of a different community. So I'm thinking here of reporters, for example, Julia Angwin from ProPublica and the Wall Street Journal, who did this expose several years ago into the most commonly used software for criminal justice risk assessment in the United States, showing that its error rates were wildly disparate between Black defendants and white defendants. That if you looked at the rate of false positives to false negatives, it was dramatically different for Black defendants and white defendants. So on both of these fronts, we, I think, at this moment in history, stand at the intersection of these 200-year-long trends that are now on this collision course. We are going through an incredible acceleration in the capability of what machine learning systems can do. And we're also living through this maybe less celebrated, but even more important, slow percolation of these systems into the decision-making infrastructure of modern society. They're a part of medicine. They're a part of mortgages and credit lending. They're a part of the criminal justice system, et cetera, et cetera. They are, increasingly driving the cars on our streets. And so there really is this question of, are these systems doing what we want? Now, this is not a new question by any means. It goes back at least as far as 1960. The MIT cyberneticist Norbert Wiener has this great essay called Some of the Moral and Technical Consequences of Automation, which has this very famous passage. We all know the fable of the sorcerer's apprentice. Disastrous results like this are to be expected not merely in the world of fairy tales, but in the real world. If we use to achieve our purposes a mechanical agency with whose operation we cannot efficiently interfere once we have started it, then we had better be quite sure that the purpose put into the machine is the purpose which we really desire, and not merely a colorful imitation of it. And this fear that he articulated, this concern, so many years ago, I think has really come of age in the last, let's say, 5 years. And we now know it as the alignment problem. Are these machine learning systems really learning what we think they're learning? And are they going to behave the way that we expect once we actually put them into real world use? So that is the subject of the book that I've just published, that I've been working on for the last 5 years. And it really feels to me that we are at the beginning of a transformative movement, both within the field of artificial intelligence and machine learning, and increasingly at the intersections between computer science and other fields like social science, public policy, ethics, law, et cetera. And so as part of my research, I ended up interviewing ultimately about 100 different researchers on the front lines of this problem to try to tell the story of all of the reasons that we have for being concerned, but also the tangible progress that's been made even just in the last several years, which has been, I think, equally breathtaking. So we don't have time to get into all 100 of those stories today, but I thought I would paint a little bit of a picture of what we can expect as we think about the frontier of the alignment problem and where things are today. So at a very, very rough level, machine learning systems have two major components, training data and an objective function. So they have a set of examples, and then they have some mathematically codified objective of what they are trying to learn from those examples. And so we're going to look at each side of the system in turn and talk a little bit about what can go wrong and the ways in which people are trying to meet that challenge head on. So first is the training data. As we've said, a system that learns by example is at some level at the mercy of the examples on which it's taught. And I think someone who articulates this very well is the head of AI at Tesla, Andrej Karpathy, who, as he puts it, the amount of sleep that he loses when he was doing a PhD, all of his lost sleep was about models and algorithms. And these days, 75% of his lost sleep is actually about the data sets on which these models and algorithms are trained. We're seeing something of a sea change in the way that people think about these data sets, led by people like MIT's Joy Buolamwini and Microsoft Research and Google Brain's Timnit Gebru, who have done a lot of, I think, very groundbreaking research into face recognition systems, showing, for example, that error rates even these days on commercial, major commercial face detection, face recognition classification systems can be, in some cases, 10 times higher error rates on people with darker skin types than people with lighter skin types. And I think there is really this awakening into questioning the provenance of where do these data sets come from in the first place. So, for example, one of the most widely used data sets in face recognition is called Labeled Faces in the Wild. And a couple of years ago, researchers from Michigan State started doing some digging into how this data set was assembled. And it was scraped from the web using newspaper articles. And so it has the bias that the newspaper articles of the time, in this case, it was the late 2000s, whatever people appeared in newspaper clippings, those are the people that appear in the database. And they actually sat down and did an analysis, and it turned out that Labeled Faces in the Wild was 77% male and 83% white. And the most prevalent individual in that data set, which was, again, whoever was in newspapers in the late 2000s, was the American president George W. Bush. In fact, there were twice as many images of George W. Bush in the data set as they were all women of color combined. Okay, so this has started, I think, a real awakening in the industry. And again, using this example of labeled faces in the wild, when the dataset was first released in 2007, it had this, peer review article that came out with it that said, this dataset clearly has its own biases. For example, there aren't many images that occur under poor lighting conditions, and there aren't very many faces that are viewed from above and below. However, the range and diversity of pictures present is very large. Fast forward to 2019. This same data set now appears with this giant red label that says, warning, there are no children, no babies, very few people over 80, very few people in a number of ethnic groups are represented at all, et cetera. And so this really shows a change in the way that people are thinking about this, right? 12 years ago, we were talking about diversity from the perspective of lighting and pose, and now we're thinking about it in demographic terms. There's a lot of really encouraging work on how might you, after a model is trained, try to work out whether the data set might have had some problem in it. Once you don't even have access to that data set anymore, you just have this AI system. One of the people who's done, I think, some incredible work here is Chris Olah, who works at OpenAI. And he has developed these visualization methods to inspect a model after it's already been built. And to abridge a technical story, you can basically get the model to output a sort of maximally stimulating image for a particular image category. So here we have anemone, fish, banana, parachute, screw, etc. That all looks reasonably normal. The anemone looks like an anemone, the parachute looks like a parachute. And it is very revealing to have this system kind of daydream the most banana, or whatever it might be. You can also use this to detect bias and potential safety problems. So for example, if you ask it to output dumbbells, you see that these dumbbells come with disembodied flexing arms attached, which is kind of surreal and it makes a certain degree of sense. But this should alert us to the fact that our model, if it's only used to seeing dumbbells attached to flexing arms, might not recognize dumbbells on the ground, might not recognize them if they're on a rack. And this could, you can imagine this kind of thing, if it were in a car, could be a potential safety issue. These data set issues can be extremely subtle and very sort of cross-cultural. One of the people who I think has done some very important work in this area is Bean Kim from Google. She has a method which we can get into later in the Q&A if you want to know the technical details, but it's called TCAV, and it allows you to determine the importance of these human concepts to a model's categorization. So you can see, stripes are important in categorizing something as a zebra. A white coat is important in categorizing someone as a doctor, etc. She looked at some of the models that Google had built, and she found that the concept of something being red was intrinsic and critically important in the model labeling something as a fire truck. Okay, well, that sounds reasonable, at least from my point of view, coming from the US. In the United Kingdom, many fire trucks are in fact red, but not in Australia, where fire trucks are white and neon yellow. So this indicates that this model would not be safe to deploy in a self-driving car, let's say, if you were going to be using it in Australia. So these sorts of transparency interpretability methods are, I think, one of the most encouraging parts of that story. This is Dario Amade from OpenAI, who leads their safety team there. One of the dataset issues that's most troubling for people who are thinking about kind of the farther future of AI is this problem that's called robustness to distributional shift, or robustness to distributional change. Broadly speaking, if you train a model on one situation and then you deploy it into another situation, can the model have some sense of danger, that it doesn't know what it's doing, right? If you train a model on white faces and then you deploy it on captioning albums of photos of black faces, shouldn't it know that it doesn't have a good reference point in its training data? Or if you deploy something on American fire trucks, or you train it on American fire trucks, deploy it on Australian fire trucks, shouldn't it at some level realize that this distribution has shifted? And that has been a critical problem in not just the bias and ethics side of the field, but also in the actual safety. So in 2018, there was a self-driving Uber car that killed a pedestrian in the city of Tempe, Arizona. And the National Transportation Safety Board review showed that one of the major contributing factors to this accident was that the model had a data set issue, which was the data set of pedestrians that it was trained on did not include jaywalkers. All of the pedestrians that it was categorizing during the training phase were people crossing at crosswalks and intersections. And so when it encountered someone crossing a road in the middle of the road, it didn't really know what to expect. It didn't have some sense that that was a place that people could even be. There was also this problem where it had been trained specifically on images of pedestrians and images of cyclists. And this particular, the victim of this accident was a woman walking a bicycle. And so the model didn't have an easy category into which to categorize what it was seeing. And there are many issues here of data set bias, et cetera. But one of them is this question of how do you recognize that you're out of your distribution? This is, I think, a canonical intrinsic human ability to know when you are uncertain of something. There's been a huge push within the field of machine learning to develop models that have this capacity to know when they don't know. One of these issues in machine learning is called the open category problem. Let's say you are developing a system to categorize different bugs. Well, there are many, many, many things in the world that are not bugs at all. And so even if you have built a system to categorize bugs, it should still have what's called an open category. If you show it a stick or a leaf or an amoeba, it should know that it doesn't belong to any of the categories on which it has been designed. And this is the center of the research of Tom Dietrich, a computer scientist at the University of Oregon. And here in the UK, Yaron Gall at the University of Oxford has been working on models of statistical uncertainty for these networks, so that not only should a network be able to tell you what it thinks an image is, but it should have a precisely calibrated and an accurate probability associated with that. So the question is, having begun to develop these models of uncertainty, of what a model doesn't know, what do you do? And here I think becomes here's where we transition from the actual computer science into the ethics. What do you do? What action do you take when you know that you don't know something? So this comes up in medical ethics. So there was a case in 2017 where the University of Miami Dr. Gregory Holt had a patient come in unconscious with this tattoo that said, "Do not resuscitate." And this is almost a textbook medical ethics example, but you never expect it to actually happen to you if you're a doctor. You can't talk to this patient. You have no idea how serious they are about what they wrote in the tattoo. Did they lose a bet? Does it sincerely express their deepest wishes? What do you do? And in particular, Holt advised his team to take this principle of not making an irrevocable action in the face of uncertainty. And I think that's a really interesting ethical principle. This is something that also comes up in philosophy of law and legal ethics. So Cass Sunstein from Harvard has written a lot about the law, at least in the United States, has specific protections for what are so-called irreparable harm or irreversible harms. How do you know when you're in that situation where you have to make, in this case, a preliminary injunction versus just following the normal course of action? This is also a set of issues that are really coming to the forefront of academic philosophy. Just a matter of months ago, a new textbook came out by Will MacAskill of Oxford and his colleagues called Moral Uncertainty, that deals with this question of how do you decide what actions to take ethically when you don't even know what ethical system is right? Are you a utilitarian? Are you a deontologist? Are you a virtue ethicist? What system, not what system do you choose, but what action do you take knowing that you don't know which system of ethics to even believe in? Can you still make some kind of decision about how to practically act in the world? So I'm very intrigued to see this intersection between some of these questions that have existed in medicine, in the law, in academic philosophy, now really starting to come to the forefront as we are developing models that know they don't know, but they still need to make some kind of action. So the second area is rather than the actual data set on which the model is being trained, what is the objective function? What is the goal of the system when it is given those examples? This is something that has begun coming up in a very acute way in the criminal justice arena. So UC Berkeley computer scientist Moritz Hard has begun really scrutinizing the objective functions that are used in criminal justice system. So to even say of a model to predict, let's say, the likelihood that a defendant will reoffend if they're released early from prison, how would you actually mathematically define fairness in this situation? So the classic definition is what's called group calibration, which says if you're given a score of 8 out of 10 risk, then you should have the same probability of reoffending as someone else who is rated an 8 out of 10, regardless of, let's say, your race or your gender. And that has been kind of the classic definition of fairness that's been used by criminologists for several decades. There are other new statistical definitions that are being explored. For example, things like so-called equalized odds or equalized opportunity that look at the error rates, the false negatives, false positives. So for the people who are miscategorized by the model, are people of one ethnic group, let's say, more likely to be false negatives or more likely to be false positives? And these sorts of definitions have been gaining prominence, which has then led to this computer science question of, can we build models that satisfy all of these equally desirable, equally intuitive mathematical definitions of fairness? And people like John Kleinberg from Cornell, Alex Choldachova from Carnegie Mellon, Sam Corbett-Davies from Stanford. A number of people have been looking into this from the mathematics and statistics communities. And unfortunately, the answer is no. It turns out to actually be mathematically impossible to construct models that meet all of these seemingly equally desirable notions of fairness. So what do you do? Well, this is really a conversation that has to happen in the realm of public policy. We have to decide which of these metrics are more important than others. What are the trade-offs that we're willing to make? But I think there's an even bigger question here as we think about what the objective is of this prediction system. A lot of these systems are designed to ostensibly to predict reoffense. Will someone commit a crime? But we can't actually measure that. Instead, we can measure rearrest and reconviction. But those things are meaningfully different. This was something that came up in the 1930s during the very first use of this technology in the state of Illinois. You had conservative lawmakers, in this case, Elmer Schneckenberg of the state house, arguing just because someone isn't caught committing a crime, they then go into the data set as having made good. And the data, the model trained on that data set will recommend releasing more people like that. So that doesn't seem right. Nowadays, you're much more likely to get the same argument coming from the left, from progressives, arguing, now, wait a minute, just because someone is wrongfully arrested and wrongfully convicted, they're going to get put into the data set as someone who did reoffend, and the model will recommend detaining more people like that. And really, it's the same argument. The political valence is flipped. But this critical difference between what the model is supposed to predict versus what it can actually measure, I think, really comes to the forefront in the domain of criminal justice. There's also this question, training data are often referred to as ground truth, and yet in many cases, they're really not the ground truth. So this is Tesla's Andrej Karpathy again. In his grad student days, he was one of the human guinea pigs, you could say, for image classification, where he was himself trying to determine, is this picture, which kind of dog breed is this, or which kind of flower is this? And after painstakingly working on this for several weeks, he was able to get up to an accuracy of, I think, 95%. But 95% with regard to what? Not the truth, but the consensus, because the data set was built on what random other people on the internet said that something looked like. So the computer has no idea if something is, a lily versus a tulip versus whatever. All it knows is that people on the internet clicked on it and said that it was, right? So that's not truth, that's consensus. Scholars like Microsoft's Kate Crawford have pointed out that this can become extremely problematic in cases where the model is trained on something, almost purely subjective. So for example, the ImageNet data set on which some of these models were trained had not only things like containership and dust mite and whatever, but it also had these subjective categories like failure, loser, non-starter, unsuccessful person. And it contained images that people on the internet said looked like losers. Well, what does that mean? I mean, what are we training these models to do other than to represent the stereotypes and prejudices that exist in the culture? I think it's really important to actually think about how the model is deployed. In this case, there's models like Compass that are specifically designed to predict whether to detain someone pending their trial or not. The models explicitly say they are not to be used for sentencing. Sometimes they still are used for sentencing anyway. And this, I think, suggests to us that we need something in machine learning close to what we have in medicine of, important, take this, use only as directed. Then I think we need something like that increasingly for machine learning as well. There's a difference between someone's risks and their needs. The instrument that's used in the United States tries to distinguish this by using colors, red versus green. Red meaning they are, likely to commit a crime, et cetera. Green saying something like, well, they have a drug dependency issue or they don't have a good family structure. That's not necessarily a reason to jail them, but it indicates something about what they need from society. And yet, despite putting it in green, many judges just decide that this is all the more reason to lock someone up. So there's a really delicate thing here between kind of the actual user interface design and how the model gets used in practice. There's also, I think, this very critical question of once you build a predictive model, what real-world intervention is that model designed to support? So if you predict that someone is at high likelihood to fail to appear in court if you release them, well, what do? One answer is you can incarcerate that person, right? In that case, you can force them to appear by incarcerating them. Another solution might be send them an SMS message the morning of their court appointment, reminding them that they have a court appointment. And there's an increasing body of research that suggests that this is actually perfectly effective. And so this is kind of outside the question of the predictive model itself, but is what do you do with that prediction? And I think in some cases, those are the most critical ethical questions there are at that interface between the model itself and how that model plugs in to the existing system. I'll just touch on this very briefly, but going back to this Google Photos Gorillas example, the objective function that's used by a lot of image classification systems is something called cross-entropy loss, which basically assigns a constant penalty to any miscategorization. So if you miscategorize any X as any Y, you get negative 1 point. But that doesn't really seem to fit our intuitions. In fact, it's probably the case that there are certain miscategorizations that are 1 million-fold more harmful to users, to society than others. How do we capture that? And so a number of computer scientists, including Stuart Russell at Berkeley and others, have said maybe we should treat the loss function, this loss matrix, as itself a machine learning problem. That before the machine learns how to categorize things, it first needs to learn what the human penalties are for making certain kinds of mistakes and not others. And that's an open area of research. So thus far, we've been talking purely about a kind of system called supervised learning, where you show a number of examples one at a time and you try to categorize them or classify them. I want to say a few words here before we wrap up about what's called reinforcement learning, which is about taking sequences of actions in order to gain some kind of points or reward. And this is another main category of machine learning system. It's what you might have seen, computers playing Atari, computers beating the world champion at Go. It's what you see driving a lot of the revolution in robotics right now and self-driving cars. And there is this incredible progress at systems that can learn to take these extended sequences of actions in order to get some kind of reward, whether it's a high score in an Atari game or maximize their probability of winning a game of Go, et cetera. Increasingly, and I think this is less appreciated, social media companies are using reinforcement learning to think about how their systems interact with people. So this is a white paper from Facebook talking about how they use actually the exact same model that was used for the Atari game playing to fine-tune notifications that they send to human users. So we are now entering this weird world where, in a very real sense, we are the Atari game that social media companies are learning to play. And so that, I think, prompts us to really ask this question of what is the reward function? What is the points in this, so-called video game? And will maximizing those quote unquote points really give us the behavior that we want? So this is the alignment problem in the reinforcement learning context. Can we create a scoreboard or a point system such that we incentivize the behavior that we really want to see? And there are some very well-known cases of failure in this. This is a research project from OpenAI where they tried to train a boat to win this boat racing game. But it turns out there was a little harbor where you could just kind of drive in circles forever and accumulate these tiny little power-up points. And their program learned to drive in circles forever and get an infinite number of points, but it completely ignored the actual race that it was taking part of. There are other video games that have been a real challenge for researchers because they don't give enough points readily enough. This is one called Montezuma's Revenge. And so how do you make progress in an environment where you don't really get very much feedback at all? How can you still give the system a sense of whether it's going in the right direction or not? This part of computer science is full of these really colorful cautionary tales. One of my favorites comes from a group of Dutch researchers who were developing a virtual bicycle. And they were trying to incentivize this bicycle to reach a goal. And so they decided to give it these little points every time it made forward progress toward the goal. Well, that sounds pretty good. What could go wrong? What was the loophole that the system learned to exploit? Well, it turns out they forgot to subtract points when you were going away from the goal. And so their system just learned to ride the bike in circles really, really, really fast, because the 50% of the time that you're making progress towards the goal, you're getting rewarded. And it's easier to just go in circles than it is to actually get somewhere. A similar cautionary tale comes from David Andre and Astro Teller from Google X, who in some of their graduate work were looking at getting robots to play soccer. And so they had included this little bonus reward for taking possession of the ball, because taking possession of the ball is kind of a necessary precursor to scoring points. They thought it would kind of encourage the robot to do the right thing. The problem was it's a lot easier to take possession of the ball than it is to actually score a goal. And so their robots learned to just hover next to the ball and vibrate their paddles, just repeatedly taking possession of it and earning these kind of micro incentive rewards. So there is a long history in computer science of these minor disasters, some of them actually comic, on what happens when you kind of misspecify the reward function you want the system to match. And so there has been this big movement in computer science of how do we get away from this problem of manually specifying this reward function? One of the schools of thought here is that we should simply have our robotic systems imitate us. We shouldn't specify that there are these points and rewards in the environment. We should just have them imitate us. There's a long-standing cognitive science into how babies learn to imitate, and this appears to be something that is very hardwired into us evolutionarily. It's also a major part of how AI functions these days. So every Tesla car comes equipped with something called shadow mode, where the whole time you're driving it, even if you have autopilot turned off, it is still pretending that it's driving the car and comparing all of the actions that it would have taken if it were in control to the way that you actually did drive it. And it's using that to kind of update itself and drive ever more like the way that you yourself drive. This is a really active area of research. There are a lot of interesting pitfalls and ways that this can go wrong, and we can get into the computer science of that if you're curious. But there's also, I think, a really interesting intersection here with ethical philosophy. So there's a problem in philosophical ethics called possibilism versus actualism, of should you always take the action which is the absolute ethically best thing to do in that moment, even if it puts you in a position where you know that you will later fail. you agree to do something for someone, but you know that you're going to let them down. Should you still agree? Because it's the right thing to do to agree. This is an active question in ethical philosophy that's been going on since the 1970s. Also, the New Zealand ethical philosopher Rosalind Hursthouse has talked about virtue ethics as a kind of imitation, and has talked about the good and the bad of thinking about acting virtuously or ethically as a form of imitating these ethically great people. So here, I think the computer science of imitation and the ethics of imitation are intersecting in a really surprising and, I think, fertile way. The last thing that I want to mention on the computer science side is ways that systems, rather than being handed an explicit objective, rather than merely imitating us, can observe human behavior and try to make a guess as to what it is that humans are trying to accomplish. And this is known as inverse reinforcement learning. So to make a long story short, if you observe someone driving, this is UC Berkeley's Peter Abeel. In his graduate work, he was creating this driving simulator. And the computer system would observe him driving in this little toy world. And it was very difficult for the system to figure out how to imitate him. But it was very easy for the system to figure out what he was trying to do. It could easily identify that he wanted to avoid hitting other cars, that he wanted to move forward, that he wanted to, keep into the proper lane when possible, except when passing. And this has been part of a 20-year story of systems that are able to infer humans' objectives and humans' values and then pursue those objectives themselves. Abeel was part of a team at Stanford that taught these helicopters to do these incredible tricks by watching human RC pilots and figuring out, even when the human pilots couldn't actually execute the trick, the computer could figure out what they were trying to do and do it better than the people could. The next generation of students, people like Chelsea Finn, are doing some pretty amazing work in robotics, where you can just move a robot and get it to start filling a dish rack full of dishes. The robot will figure out what it thinks you're trying to do and then can complete that action. There's a lot of really interesting work on cases where even if you can't demonstrate the behavior, as long as you recognize it when you see it, that alone might be enough. And so one of my favorite examples here is Paul Cristiano from OpenAI, Jan Leica from DeepMind, built a model where they would just show you video clips and say, which of these video clips of this robot wriggling around is slightly closer to what you want to see? And one of the examples that they used was doing a backflip. They said it's easy to know a backflip when you see one. It's hard to do one. It's hard to specify numerically what a backflip looks like, but if you see it, you can identify it. And so they would show people these video clips initially of the robot just moving at random. They'd say, which of these looks more like a backflip? And as you start to make choices like, left video, right video, left video, it starts to build this model of what it thinks you think a backflip is. And then it gets better and better and better at doing that. And by the end, after just about an hour of providing this feedback, their virtual robot can do these kind of gymnastically beautiful backflips, tucking the leg to spin faster and sticking the landing. And to me, that is just a very, very encouraging sign that we can impart into these systems the things that we value, the things, even when we can't demonstrate those things very reliably, we can't articulate them directly in numbers. The instructions of their experiment just said, look at the clips and select the one in which better things happen. And I think that is a beautifully open-ended description, right? And there are many, many technical details here to overcome, but that really suggests to me a path forward. And I think there's something very hopeful here. But there's also this kind of lingering ethical question of, even if we have systems that can learn these very complex human values just by asking us, which of these scenarios is better, that still leaves us with this fundamental question of who decides for whom, right? Who decides and who decides on behalf of whom? And, for better or worse, that is one of the oldest ethical questions there is, and I think is going to only be more important going forward. So to summarize, I think solving the alignment problem will be the defining human project of the coming decade. I think it's going to require a kind of interdisciplinary expertise at the boundary between computer science and all of these neighboring disciplines. I think we have every reason to be concerned as well as encouraged. This is, in the philosopher Nick Bostrom's words, philosophy on a deadline. We really do have to get this right, and we have to get it right quickly, because this is moving through society at a breathtaking rate. But it really does feel to me that we are rising to that moment, and there is an incredible movement mustering at the intersection of these issues. And to me, I think is one of the most important and one of the most exciting things that's happening in all of science. And I think if we get it right, it will also involve, I think, a profound and revelatory encounter with ourselves. What are the values that we have? What are the norms that we want to uphold? And how do we want to do that? My mind goes back to this radio address from Alan Turing in the 1950s, where he was talking about very early experiments teaching a machine to do what he wanted. And he said, it's always learning too slow, or it's learning the wrong thing, and that a tremendous amount of intervention is needed before it gets the right idea. And one of his co-panelists interrupts him and says, "But who was learning, Turing? You or the machine?" He replies, "Well, I suppose we both were." With that, I'll take your questions. Thank you very much.
Thank you very much, Brian. That was absolutely fascinating. And one of the weirdest things for me, actually, was that we were learning from you so many things that we didn't even know we should care about yet. I mean, yes. We've got to think about this stuff in advance.
I think there are many people who, went through their careers assuming that they were in a non-technical field. Maybe you were a judge, right? You sit on the bench after a long legal career. You're making decisions about should people be paroled, or, well, that would be on a parole board. You're making decisions about, arraignment, pretrial detention, and so forth. You probably didn't have a statistics training or machine learning training, but now suddenly a new law gets passed. And, for example, here in California, there was a law passed that said all pretrial detention decisions have to be done using an algorithmic risk assessment instrument. So now you're sitting on the bench, you start getting these printouts that say, okay, the such and such model says this person is a 7 out of 10. What does that mean? Yeah. How does that inform your judgment? What do you need to do? And so I think there's a lot of people in or you're a policymaker, right? And now all of a sudden you need to think about how to regulate these things. So, I mean, for me, part of the motivation in writing the book was we need to rapidly, get our minds around this, even for people who are not scientists, not in, computing at all, don't necessarily have that background or that orientation. This is, I think, just increasingly part of what it means to be a citizen in the 21st century. It's going to affect us all. Absolutely.
Well, a lot of people are very active through your talk there. They engaged a lot. They're very interested. They've got some questions. The first one is from GT. GT, I'm going to switch you on there. Can you speak?
Yes, can you hear me?
Yeah, I hear you.
Hi. My question really was this: to what extent is the alignment problem not just a consequence of the data set, but also the fact that we don't quite know how machines learn? In other words, we don't know precisely what's happening when machines learn. So that it's only when they make a mistake, you then get a clue, oh, they've learned it this way. But of course, making a mistake as in the person who got killed by the self-driving car might be too late. So is that the black box problem also a difficulty?
Yes, that is very much connected to the reputation that deep learning in particular has as being a black box. And I think you see this in many places. I talk about in the book, even in the United States Department of Defense, people in the intelligence community getting these reports that say, the computer has analyzed this satellite imagery and it says this thing kind of looks like a weapons depot. Should we blow it up or whatever? And a human analyst has to sign off on that report and authorize a strike or not. And increasingly, these analysts were complaining, like, my moral authority is going behind this. My neck is on the line if we screw it up. It's on me if we hurt someone innocent. But I don't know what to do with this data that I'm getting. It just says the model said this was a, something percent likely something. What does that mean to me? How do I actually decide for myself whether I feel comfortable authorizing something? You see the same thing in medicine, right? The diagnostic system says this looks benign, this looks malignant. How do you feel comfortable that the model's learning what you think it is? And there has been an incredible progress in trying to pop open the lid of that black box, so to speak, and actually inspect the inside of a model. So I talked a little bit about that with Chris Ola's work with the dumbbells, Bean Kim's work with the fire trucks. There's this class of methods called Saliency Maps, where if you show an image to the computer, you can get sort of a heat map that shows you which parts of the image were critical in determining the classification that the machine made. That's another way to catch some of these problems, hopefully before deployment. So in the medical realm, it turns out that one of the classification systems for whether skin discoloration was malignant or not, one of the most important things the model was looking at was it was looking for whether there was a ruler in the photograph or not, because it turns out that medical textbooks have rulers in their images of tumors and lesions and things, to indicate scale. And so the model mistakenly learned, oh, anytime there's a ruler, it's cancerous, because all the medical images of cancer have a ruler in it. And so it's cases like this where saliency methods are one way that we can hope to kind of catch these things before they actually manifest. But it's an ongoing research area. It's very much an active area.
The next question is from Emily Jost. Are you there, Emily? I'm going to allow you to talk here, unmute you. Are you there?
Sorry. Yes, I am.
Great, fantastic. Go ahead.
Hi. Yeah, I was just interested in the fact that all of the machines are learning from visual input pretty much exclusively. And I wondered if it's not really a question about the ethics, it's a question about how all those missing senses that we're not training. You didn't mention anything about that. I just wondered if you could say a little bit about how can a machine learn using the sense of smell, for example, or any of the other human senses?
Yeah, I mean, even just within the visual domain, there is a lot of, I guess I would say, controversy about the fact that these models are trained using still images. So they don't understand depth perception, and they don't understand that objects persist over time, or things like that. So even just moving from still images to video is considered, a pretty major step. Part of what you're talking about is known as cross-modal. So there are these purely visual models. There are purely linguistic models that are designed on huge corpora of text. Can you fill in the missing word in a sentence? There's been a lot of progress there with language models. And so a lot of people are saying, well, is there a way to put these two things together? Isn't it weird that this model can achieve incredible performance at, filling in the missing word in a sentence without actually knowing what any of these things mean? What do they refer to in the world? And to me, there's a very, very interesting philosophical question here. There's this question in cognitive science of what's called embodied cognition. Basically, is human intelligence and the human conscious experience kind of inextricable from being in a body that lives in space and moves around and bumps into things, etc. AI is giving us, I think, an empirical crack at that question. So we are going to find out. Can you build an artificial general intelligence without giving it the sense of sight, or only giving it the sense of sight? So we'll find out. I think this is one of the most exciting times to be a philosopher of mind that there's ever been.
Next question is from S. Vaughan. Are you there, S? Are you still with us? I could ask the question for you if you're not. It's a good question. Okay, I'll do it just in case he's just run off to get another cup of tea. He said, as health systems and hospitals have become focused on profits, as in business, algorithms dictate the faster patients are processed, then the more profit. Thus, the goal of the AI systems serve the corporations while harming individuals. How to persuade corporations to find a better balance?
I think this is crucial. So the alignment problem, as people in AI ethics and AI safety think about it, is primarily about the alignment, so to speak, between the designer of a machine learning system and the system itself. Does the system do what that person wants? And so one of the decisions that I had to make in writing the book was I didn't write about autonomous weapons, even though that's a very active area of AI ethics, because I don't view autonomous weapons as an alignment problem in the technical sense. If I tell the missile to kill someone and it does, there's no alignment problem in the technical sense. The system did what I intended. There's no sort of sorcerer's apprentice problem, at least on its face. But I think there's a very critical thing to maintain in focus, which is the language of the alignment problem was borrowed by the computer science community from economists who have thought about alignment in terms of aligning incentives within a corporation or within parties in a contract. So the alignment problem was always a human problem. It was, are these group of humans behaving in a way that's in sync with this other group of humans? And that is the form of the alignment problem that we are going to be left with, even if we can confront the technical challenge. So even if the health insurance corporation, to use your example, is able to deploy software that doesn't mistakenly classify the ruler as a tumor, et cetera. It doesn't have a data set that's only people from a certain ethnic group or whatever. We can solve all of those problems. We're still left with the question of, is the actual business model of that corporation aligned with the interests of the patients? And so in that sense, it is alignment problems, all the way up, if you like. And those, that's really the problem of governance, of political science, political philosophy. The discouraging story is that those problems have been around a lot longer than the technical problems, and we still haven't solved them. So I think I really do feel that a reckoning of governance is awaiting us on the other side of this kind of immediate scientific challenge.
Okay, I've got two questions here also from George Chiesa. Apparently he's in a really noisy place, so he wanted me to ask those for you. I'll go through them quickly, and perhaps you could answer them both at the same time, so that everybody else gets a fair shake too. It's a good question. He said, should Ethics 101 through 109 be a prerequisite of being allowed into university studies? Are we teaching the right people, those who can learn ethics, just as algebra before TensorFlow? So I think actually the modern world is making us realize that people do need an awful lot of cross-disciplinary subjects now. The specialization where we're ending up in sort of like little dark tunnels. And he also said, in the Cold War era under SALT, encryption was classified as a weapon-controlled export. Since badly designed or implemental AI can affect people way more than weapons, do we need to check people's understandings of ethics and mental health? Just like in safer countries, people would have to be assessed before they're allowed to drive or carry weapons. Should we vet whose society gives access to AI technology?
Great. Yeah, I mean, I think the regulatory aspect of AI is quite challenging. The analogy with cryptography is interesting because there you're talking about essentially regulating intellectual property. Often the analogy people make in AI safety is with nuclear regulation. So, we have treaties that regulate which nations can get access to enriched plutonium, et cetera, and we can try to regulate that, and we're not fully successful, but it's reasonably successful so far. It's harder to know with AI because it's just ideas that appear in academic papers that are free for everyone, plus computers that you can buy sort of commercially. So, to make a killer drone, all you need is, a quad rotor and a knife and a face recognition thing and slap them together. So from a regulatory standpoint, there is no enriched plutonium. There's no kind of single thing that you can easily regulate that. So I think that there's a huge regulatory challenge there. To the question about ethics, I think we're really going through, for me, part of the encouraging story that I ended up finding as I was researching the book was that we really are living through, I think, an ethical awakening for the field of computer science. That in even just the last several years, almost every undergraduate computer science program has realized they need some kind of ethics course. Some kind of ethics curriculum for students in data science, machine learning, et cetera. More broadly, certain people have argued that if you're trying to become a civil engineer, if you're trying to build bridges, it's not like there's one class that you take as a freshman that's like the bridge safety course. And that's where you learn that bridges aren't supposed to fall down. And then the rest of the time you talk about making bridges efficiently and cheaply and whatever. No, rather, it's on the contrary, that safety is intrinsic to what your profession is. So there's no bridge safety course. It's just understood in everything you do that to build a bridge is to build a safe bridge. So perhaps we need something like that in computer science that is not a specific unit of curriculum, but just sort of intrinsically part of the field. We may get there, but I think for now, just putting something into the course requirements is a good start, and we are seeing that.
Okay, we also have a question from Francisco Diego. Francisco, are you there? I've just switched your sound on. Hello, Francisco,
yes,
are you there?
I'm here. Yes, thank you very much. Fantastic lecture. It's a kind of an eye-opener for some of us that are a bit behind on all these things. Thank you very much.
My pleasure.
Now, I have been to several of these kind of topics, and we are talking about artificial intelligence. Shall we refer it to an artificial knowledge instead? We are talking about ethics and wisdom. How about artificial ethics or artificial wisdom? Is it a possibility of developing within the artificial side the ethics that we are talking about? It's a very tricky thing because we are dealing now, it's like playing God, if you like. I mean, it's very interesting. I don't know, you can elaborate a little bit, please. Thank you.
Yeah, I think that's a great question. And this is something that has been echoed by some of the pioneers from the 20th century. So there's a wonderful book by MIT's Joseph Weizenbaum in the 1970s called Computer Power and Human Reason, where he argues that there are certain types of decisions that should be reserved for humans because humans alone possess the kind of moral responsibility for making a decision like that. The work of Norbert Wiener, who I mentioned in this talk, he had a very beautiful essay where he said, engineering in particular has been concerned with know-how, but it should be concerned with know what, right? That it is a field about taking for granted the objective you want to achieve and just asking the question, how do you achieve that objective efficiently? As opposed to what is the correct objective in the first place? We've begun to see some of that changing within computer science. So the fourth edition of the canonical AI textbook, which is called AI, A Modern Approach by Stuart Russell and Peter Norvig, just came out, I think, several months ago. And every time a new edition of this book comes out, it's a major event for the field. And this was one of the major changes from the third edition to the fourth edition, was they said, we wrote this 1,000-page book about, let's just assume you have some objective. Here are all the ways that the field has for how you can get that done. Instead, we're now at a point where perhaps the technology has advanced to the point where we can take for granted that you can basically achieve whatever objective you want in this kind of sorcerer's apprentice way. The real question is, what should your objective be? And so we are starting to see the field move in exactly the direction that you suggest. I think it can't come soon enough. It can't come quickly enough, but that is the direction things are going.
Okay, thank you. Thank you very much. I can imagine all this technology applied to, for example, protecting the environment, avoiding wars, avoiding refugees. I mean, making a better world, for goodness sake. I mean, it's not for the industry, it's not for the business, it's for the planet. We have the technology to do that. We should be working on that.
I completely agree. And I mean, this is something that's, I think, a challenge for people who work in peer research. I went to a panel at the AAAI conference a few years ago, and one of the researchers was saying, you know, I want to do ethical AI research, but how can I be sure that the work that I do doesn't get adopted for some other purpose after the fact? You know, I design an algorithm for search and rescue that someone else uses for search and destroy. How, you know, it's the same algorithm. It's just, you know, whether you help the person or harm the person. So that is, I think, one of the challenges is just how general a lot of this technology is. It really allows us to use it for both of those things. I mean, there are many computer scientists that have done amazing work in, for example, looking at deforestation or looking at anti-poaching, et cetera. So that work is being done. But I think it is both a question of, is it possible to prevent techniques like that or algorithms like that from being used in a harmful way? Can we try to prioritize the use for these good objectives? That, I think, gets us back to the question that one of the earlier people asked about, you know, governance and just what is it we want our corporations to be doing? What is it we want our governments to be doing? I think that really comes to the fore.
Next question is from Norman Hanson. You still there, Norman? Hiya, Norman.
Mute. Yeah. Sorry.
Yeah, you're with us. There you go.
Took a second to get the unmute button.
Okay.
Yeah. Great. Yeah. So my question is sort of are our models far too narrow at the moment? And actually, although we're saying the technology is advanced enough to do certain things, if you take, for instance, an example of looking at tumors, a model might look at tens, hundreds of thousands of tumors and benign lesions, but it still isn't asking questions about, say, the ethnicity, the gender, other factors, you know, that might affect what that tumor or what that picture is actually showing it. And it's the idea of general intelligence, where a doctor would sort of say, oh, well, this person has been exposed to carcinogens in the past. You know, that might explain why they've got this.
Yeah, there are a couple different things there. One is that traditionally machine learning systems have looked only for correlations as opposed to causation. Yes. And so there's a lot of work that's happening in that area. The other thing is, to your point about narrowness, there is a set of techniques that are called multitask learning, which basically is you ask the model to make not a single prediction, but a host of predictions. So this is kind of like what you were describing. This has been very useful in medicine. So for example, there was a story I tell in the book. There was a project in Pittsburgh in the 1990s to use neural networks to help triage patients with pneumonia. And one of the strange things that their model learned was that if you are a pneumonia patient who also has asthma, then on average, your health outcomes are better than the average person who does not have asthma. Therefore, we don't need to worry about the people with asthma. And that just doesn't make sense if you think about it intuitively. Why would it be good to have asthma if you also have pneumonia? it turns out that this was a real correlation in the data set, but it was only because the asthmatic patients with pneumonia were seen as so critical, or in such delicate condition that they received the highest priority care. They were treated, with the greatest urgency, et cetera, et cetera. And so, yes, on average, they did actually have a slightly better outcome than the average non-asthmatic person, but it was precisely because they were treated so seriously. Well, the model didn't know that, and so the model just said, they have pretty good outcomes. Let's let them go home. One of the things that you could do to solve that is what I mentioned earlier, multitask learning. So instead of just predicting whether they live or die, you could also predict, for example, what their health insurance bill is, or how many days they're going to be in the hospital. So the multitask system might say, yes, I predict that these people are going to survive, but I predict that they're going to be in the hospital for weeks and have a $500,000 bill. Well, that tells you that, something went wrong, that they're a high risk person, even if their actual outcome was okay. And this is something that has become more and more widely used. And in fact, there have been several medical breakthroughs stumbled upon accidentally just because a team was using multitask nets. So there was a group that was looking at images of the eye, and they were predicting whether you had certain types of disease or degeneration based on a scan of your retina. And just as a kind of backstop, as a kind of normalization technique, they did this multitask learning thing where it would predict not only what it thought your eye condition was, but also your age, your gender, blah, 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 your blood pressure, all these other things. And they were doing it just to kind of broaden what the model was doing and make it not so narrow. But it turns out that you can actually determine someone's biological sex from their retina, which medicine didn't know until the model started doing it. And they were like, no, wait a minute. This thing is 95% accurate at predicting sex. That is not what we expected. So there are these little serendipitous moments that come out as well. But to your point, yes, that broadening what these models are doing is, I think, a very important piece of the puzzle.
Okay, we've got a little less than 10 minutes left, so I don't know if we're going to get to the bottom of all of this. This is a very, very active Q&A session. I think everybody's really engaged with this. It's Michael next. Are you still there, Michael? Michael?
Yes, hello, can you hear me?
Cool, okay.
Hi.
Okay, great. Well, thank you very much. What a fantastic talk. So interesting and very.
I appreciate that.
Thank you. I'd just like a slightly more practical view from you about the state of AI. I mean, you've described a particular area where there are lots of ifs and buts, where it sometimes works and sometimes doesn't. There are other areas of AI where it works incredibly well, like playing Go. Yeah. And there are some other areas where it works incredibly badly, like Siri and Alexa and chatbots. Can you explain a little bit why some things don't work so well and why some things work better?
Sure, I can try. In fact, my first book 10 years ago was about chatbots and why chatbots are so bad, which is called The Most Human. And so I had some firsthand experience of participating in a Turing test competition against a bunch of chatbots where I was trying to persuade a panel of judges that I was not a chatbot. I was, in fact, the actual human, not a chatbot claiming to be human. But even in the time since that book was published 10 years ago to now, there has been an incredible amount of progress in natural language processing. I would say really since the end of 2017. So something that I didn't talk about explicitly in the talk has been the rise of what are called transformer networks. So to wave my hands a little bit, transformer models have to do with attention. That is to say, they allow a network to focus on a particular subset of its input and kind of emphasize that. Transformer models have been hugely revolutionary in natural language processing starting in the late 2017. And one of the things that has, I guess, really become clear is that the limitation in natural language processing has been money. Money and electricity. So the current state-of-the-art models in natural language processing are things like GPT-3. I don't know if you're familiar with this, but it took OpenAI something like $10 million in 6 months to train this thing on Microsoft's cloud cluster. And at the moment, we're just mostly limited by time and money and electricity, which is a little bit of a weird place to be for AI, where we don't know what the ceiling is yet for our current set of techniques, because we haven't actually hit that ceiling yet. Every year, the models get twice as big and, 1% better or 10% better or whatever. And we're just still in that process of just throwing money at the problem. And no one really knows how far this goes. Are we going to be able to take these modern transformer networks all the way to something like artificial general intelligence? Are we going to hit some kind of asymptote or some sort of ceiling and we'll need a new set of techniques? Currently, we don't know. That is an open question, and there are people on both sides of that. I don't know if I have an easy heuristic to offer you about why certain areas appear to advance while others don't. I think the most general way that I could try to summarize that would be, it's a question of data. I mean, there are advances in algorithms, there are advances in the actual hardware, but I think one of the biggest things has been data. So the neural network revolution, or the revival that we saw in the 1980s, Jeff Hinton, one of the pioneers of deep learning, has said, we got really excited in the 1980s that, holy crap, this stuff that Pitts and McCulloch were talking about in the 40s, this is actually going to work. But our computers were millions of times too slow and our data sets were millions of times too small. And so we didn't get anywhere. But there was nothing fundamentally wrong with the actual ideas. They were just too early. And so in particular, part of why image recognition leapt forward in 2012 was this kind of serendipitous thing that was going on in hardware, where we'd begun developing these so-called GPUs that were useful for playing video games. And then someone later found out that they were really good for doing computer vision. So now we had this kind of custom built hardware. But the bigger story, I think, was the data set. So it was not until the internet that you could easily get your hands on 10 million pictures of faces and books and cars and things. And it was not until the invention of Amazon's Mechanical Turk service that you could incentivize people, around the world to label those pictures for you at a relatively cheap price. So I think that was really the breakthrough for computer vision, was because of the internet and because of the Mechanical Turk service, it's now possible to get 1 million, 2 million, 10 million labeled pictures. A big problem with self-driving cars is, how do you get the data? You have to put the sensors on the cars and drive them around in order to even get the data that you're going to train the model on. So we're solving that problem. And then with language models, it's just a question of scraping the internet. So what websites do you go to if you want to download, multiple terabytes of text or whatever it is? And then your model is at the mercy of whatever parts of the internet it learned from, and not all parts of the internet are equally appropriate or equally trustworthy. So these data set things kind of continue to be an issue. But I think one of the most difficult things for AI is going to be making progress in these domains where we don't have a lot of data. So for example, you want a robot to do surgery, you don't want it to learn by trial and error from botching 500,000 surgeries, which is the way that it learns how to play Atari. So that's going to be, I think, one of the last areas.
Okay, as we told, we can run on a little longer, so that's cool, because these questions are coming up thick and fast. There's one from S. Vaughan, which I'm going to say myself, because it also kind of relates to another question which we have. Is the ability to build in empathy to decisions being studied, which I think is incredibly relevant. And I'll also put George Chiesa, who we've heard from earlier, because he has another question, but I think it relates to that, and perhaps we could do those both at the same time. George, you there again? Hello, George, you there? Okay, no problem. Let me just absolutely make sure that I have... Yeah, no. Okay, so I'll read it out for him. He said, considering the recent memo from the top armed forces in the USA, basically telling the troops not to accept illegal orders from the president, should AI refuse to comply with unethical orders? I guess it's actually harder to define what's unethical as opposed to what's illegal. So he fairly says, who decides what's unethical? And then that ties into the previous question earlier about, can machines be empathic to something?
Yeah.
Or express empathy anyway, even if
Yeah.
they feel it.
So I'll try to do these roughly in order. The empathy question, I think, is very interesting. You know, humans, we've come to understand just in the last, I guess, 30 years that humans have so-called mirror neurons, that we have some sort of hardwired ability to feel other people's pain. And I think there's a question of, can you build something like that into a computer system? I think that some of the work being done on what I mentioned at the very end of the talk, inverse reinforcement learning, as it's known, starts to get at that, right? If you can work your way from observing someone's behavior to figuring out what motivates them or what they're trying to accomplish, then you can start to work your way to a model of what would please or displease them. It's far from straightforward. I mean, many PhD theses will be written in order to get there, but this is the kind of thing that is being worked on. I think the contribution of neuroscience is actually very critical here. So I didn't talk about neuroscience at all in the talk, but there is a very, very fascinating connection between neuroscience and reinforcement learning. In particular, set of techniques, well, I'm just deciding how quickly to get through this, but basically there was this riddle in the 1990s of, we had all these readings from dopamine neurons. We didn't have a model of what the dopamine neurons were doing. We knew it had something to do with reward, but it was not actually reward. It had something to do with surprise, but it wasn't actually surprise. It was very mysterious. The reinforcement learning community from AI came along and took a look at that data and said, oh, the brain appears to be doing temporal difference learning, which is this algorithm that we just worked out for how computers can update their sense of, how promising a situation is. Oh, I think I'm going to win the game now because of this unexpected move or whatever. So there's a very interesting case where it is the AI community coming along and offering us an explanation of how the reward system in our own brain works. So I think there will continue to be this very, very interesting dialogue between those two fields, where we simultaneously need to build systems that can model what humans care about in order to develop systems that are empathic and safe. But along the way, those very formal models are actually being picked up by the cognitive science community and the neuroscience community, and teaching us something about, that really does seem to be the way the human brain's reward system works. So there's an opportunity there to learn something, I think, very fundamental about what it is that we want and what it is that we care about. And there are a lot of connections between reinforcement learning and things like addiction and boredom and so forth. But to the question of essentially insubordination, this is very interesting because the canonical horror story that people have in their minds about AI is the Stanley Kubrick 2001: A Space Odyssey. Open the pod bay doors, Hal. I'm sorry, I can't do that. Right? This has been one of the classic horror, scenarios when thinking about AI, is the AI refusing to follow orders. And yet, as you point out, human insubordination has been a critical ethical buffer throughout human history. So one of the stories that I tell in the book is that of the Soviet missile commander Stanislav Petrov, who in, I believe it was 1983, received a warning from his computer system saying the United States has launched a ICBM attack against the Soviet Union. You need to retaliate. And his screen is flashing red, you know, launch, launch, launch. And his orders are very clear. It is not even up to him to decide to launch. He is merely to relay this information to his commander. Pick up the phone, tell the commander the computer says this. It is explicit that that is what he must do. It is not up to him to not do that. But he knows that if he does that, then his commander is going to order a strike. And something feels fishy to him. It doesn't really make sense. The American attack does not fit the pattern that he's expecting. It's only 5 missiles. Why would the US only attack with 5 missiles, etc.? And so, as he puts it, like his instructions were very clear, but nowhere did it say how quickly he had to act. And so he decided he would just wait. And he waited about 20 minutes, knowing that if he was wrong, then, you know, he was basically going to be vaporized, and it was going to be an extremely horrible situation. But he waited. And after 20 minutes, the system changed its mind and said, oh, no, actually, that was just sunlight reflecting off of North Dakota. Sorry. And probably something like 100 million lives were saved merely by someone doing nothing for 20 minutes. When their orders were very clear and the computer's instructions were very clear. And so this, I think, is a very useful reminder that as we think about AI safety, on the one hand, we don't want to have the HAL issue where we need it to do something and it refuses. On the other hand, refusing to follow orders is this critical ethical, you know, backstop that has come up many, many times in human history. And we might actually want something like that in our machines. And so this is something that many papers have been written about. I saw a lecture on this at a recent conference from the U.S. Navy, of all people, talking about, you know, the importance of insubordination, which is not the kind of thing I would have expected from the U.S. Navy. But it's an active scientific problem as well. And thinking of some of my colleagues at UC Berkeley, talking about cases where, you know, it's very double-edged. But if the computer, and this goes back to the empathy thing, if the computer can build up such a confident model of what it thinks you want, it might be able to get to a point where you ask it to do something and it says, no, you don't actually want that. You're not actually going to like what happens if I do that, so I'm not going to do that. Again, it's really a tightrope walk, but I think that's something we have to figure out.
Well, that's good to know. Thank you ever so much. This has been absolutely fascinating, and there are a lot of things that I didn't even know that we need to think about, and clearly we do, and I'm glad that people are in time rather than dealing with everything afterwards. Thank you ever so much for speaking to us this evening. I'm sure everybody enjoyed it and will go out and buy the alignment problem, How Can Machines Learn Human Values? If I could just say to all of the people who are still watching, all of our viewers this evening, remember that Conway Hall Ethical Society is a charity and it has been suffering as much as everybody else has during lockdown. So if you can afford it, please do make a donation. It's very easy through the website. Thank you ever so much for coming. And thank you to our guest this evening. Hope to see you again sometime soon. Bye-bye.